we now consider the synthesis of this molecule that I call L67. And when we're thinking about this retrosynthetically, following the guidelines from the previous lesson, the question we want to ask ourselves first is, what are the most obvious places to form bonds? That in many cases is the hardest part of the job, and in drawing this structure I have already done that for you because I have indicated the most obvious bonds to form in red. So thinking about the example from the last lesson, when we have molecules like this that have a lot of nitrogens in them, we should be looking for CN bonds as bonds to form in our synthetic reactions, because as we saw in the last lesson, they can be formed by reacting a nucleophilic nitrogen with an electrophilic carbon atom. So in this molecule, we have an imine, CN double bond, we have an amide, and then we have, moving to the left, a secondary amine that is next to a CH2. So all of these CN bonds can be formed using reactions that are in our toolbox. Specifically, imines are formed through reaction of a primary amine with an aldehyde. Amides are formed through an acyl transfer reaction of an amine with one of the more reactive acyl derivatives, namely an acid chloride, anhydride, or ester. And then finally, the secondary amine next to the CH2 can be formed through an SN2 reaction, just like we saw in the last lesson. I do want to take a moment to talk about order of operations, given that we're going to be forming 3 carbon-nitrogen bonds in the course of this synthesis. Which one do we do first and which one do we do last? The general principle is that you want to install the most reactive functional group last, because that functional group could react under some of the conditions that are necessary to install the less reactive functional group. And then the corollary to that is you're going to install the least reactive functional group first. So of these 3 functional groups, the order of reactivity is that imines are the most reactive, followed by amides, followed by secondary amines. And if you think about this, imines are readily hydrolyzed under weakly acidic conditions. Amides require strongly acidic or strongly basic conditions and prolonged heating in order to undergo hydrolysis. And we have never seen a hydrolysis reaction of a secondary amine. So therefore, in terms of the thinking backwards that we want to do in our retrosynthetic analysis, the final reaction in our synthesis will need to be formation of the imine. Okay, so let's put this into practice. What aldehyde and amine would be necessary to synthesize the final L67 molecule through formation of this imine? Okay, so the answer is the amine is on the left-hand side and the aldehyde is on the right-hand side. Okay, so is the aldehyde commercially available? The answer to that is yes. It is called 2-hydroxy-5-nitro-benzaldehyde, but the amine on the left-hand side is not commercially available, which means that it has to be synthesized. And the way we will synthesize this amine is through an acyl transfer reaction with hydrazine as the nucleophile. Okay, and the starting material, the other starting material that I have decided to use in this case is an ester to react with hydrazine as the amine. So I chose the ester as an acyl derivative for 2 reasons. First of all, hydrazine is a very, very reactive amine when it's reacting as a nucleophile. because it's got two nitrogens right next to each other. And the effect of the second nitrogen is actually to make the first nitrogen a better nucleophile. But then secondly, the ester fragment, or whatever the acyl fragment that I am starting with, would still have to be synthesized. That's still not commercially available. Hydrazine is. So therefore, in order to do this synthesis, in the first reaction, I would need an acyl derivative that is less reactive than a primary alkyl halide. And that's why I chose the ester. So I'll go into this in a little more detail on the next slide. So for the retrosynthetic analysis of the left-hand ester, this ester is then made from 3,5-dibromo-4-methylaniline plus ethyl chloroacetate. Notice I said made from, but what is depicted on the slide is this weird looking arrow. This weird looking arrow with two lines hooked up to the arrow tip is called a retrosynthesis arrow. That is the arrow that we frequently use in our scratch work on synthesis problems. And as I said, it translates as made from. So both of these starting materials are commercially available. So getting back to the point of what if I had tried to make an acid chloride instead of an ester as our acyl fragment to do the hydrazine coupling with? Well, that would have required chloroacetyl chloride instead of ethyl chloroacetate as the partner that I would be trying to react my aniline with. However, the problem would be that this molecule has two functional groups on it. Ethyl chloroacetate also has two functional groups. It has an ester and an alkyl chloride. Chloroacetyl chloride has an acid chloride and an alkyl chloride. And the acid chloride is more reactive than the alkyl chloride. The amine would react with the acid chloride to give you the amide that is shown on the slide rather than do the desired SN2 reaction. Because with acid chlorides, they are extremely reactive towards acyl transfer. Esters are much less reactive towards acyl transfer. And note, if you're trying to do a synthesis where you're taking 4 fragments and putting them together in a line, the middle 2 fragments both have to have 2 functional groups on them, because you're going to have to be forming 2 bonds to each of those middle fragments. So this issue of which functional group is more reactive is a very common issue that we will have to deal with. Okay, so once we have thought about how we're going to do the problem, now comes let's write our final answer, what we would put in down on our paper and put a box around in the forward direction. You can do your scratch work thinking backwards, but you need to put your final answer down in the forward direction. Okay, so reaction 1 is the reaction of the 3,5-dibromo-4-methylaniline with ethyl chloroacetate. Reaction 2 is the reaction of the resulting ester with hydrazine to give the amide. And that amide, of course, has an extra NH2 sticking off the end of it. Then reaction 3 is the condensation of that extra NH2, that's now the amine piece, with the 2-hydroxy-5-nitrobenzaldehyde to give the final product through an imine formation reaction. Okay, this may have seemed a little bit complicated. If you didn't get it all the first time, feel free to go back and look over this again and go through it at a slow enough pace that it all makes sense in your head. But what I think is a great take-home message for this is that a molecule that's under investigation as a potential new cancer drug, we can understand the synthesis of it using reactions that we have learned in basic organic chemistry. There is nothing exotic about this. Okay, so in this particular synthesis, all of the reactions that we formed to increase molecular complexity were carbon-nitrogen bond-forming reactions. Moving forward, we're going to consider reactions that increase molecular complexity through the formation of carbon-carbon bonds.